Hello, everyone. My name is Shannon Holmes. Thank you so much for joining me today. I know there are lots of things to choose from at the AAPM meeting, and to take time out for those of you who are attending AAPM to join us here is absolutely wonderful. It's very flattering that we would rank among your choices on the many things to watch. And for those who are not at AAPM, I also thank you for your time. It's a pleasure to be here with you today. So the topic today is our Exradin scintillation detectors. The W1 and W2 have been out for a little while, but we've just released the special configuration for MR, the W2MR. And so a little bit of the focus today is small field measurement with MR, I guess the major focus, small field measurement with MR compatibility, but I will talk about the scintillators in general as well. So it's your time, be precise. And of course, we are here at Standard Imaging to help you. A little bit of housekeeping. Those of you who have seen webinars from us before have probably seen this before, but we do record the webinars. Both our standard webinars outside of these big meetings, as well as, of course, this presentation for AAPM. If you have questions at any time, please feel free to enter that in the GoToMeeting dialog box under questions. They usually pop up for me. I'll try and answer those as I go through the presentation. But if I miss yours, I will try and circle back to it at the end. And of course, if you have to throw a question and bow out, you can always follow up via email, or the recording will be sent out to everyone within the next couple of days. And you can listen to the question and answer at that time, or any section that you missed, or feel free to forward it to a colleague or someone you want to share it with. Standard Imaging, if you don't know much about us, is based in Middleton, Wisconsin. We're just outside the capital city of Madison. It was founded a little over 30 years ago with a modest couple of products, but has grown significantly since then. We now design and manufacture a full suite of QA products for radiation therapy. So we'd be happy to talk to you about any of our many solutions. The scintillators themselves, though, are a relatively recent development, I guess, over the past few years. The purpose for choosing scintillators, though, is really the option for a fully water equivalent detector for MV photons and electrons. With these small field challenges that we've all faced as we're looking at smaller and smaller treatments, is really how do you measure the dose at that point within the field without disturbing the dose distribution or perturbing that measurement right at the point where you're trying to determine what it is. So that's where the water equivalence really comes in a big way in these small field measurements. It is not perturbing that beam, not requiring those correction factors as that energy spectrum changes. Scintillators can be made very small. They have the organic scintillators that we're using have shown dose and dose rate independence, which is another advantage as we're moving to a wide array, hopefully moving into flash at some point here, but we don't have data on that to share at this point. Energy independence also helps with those small field corrections, as we know the spectrum changes when you really collimate down to extremely small fields. The beam quality conversion factor is unity, which is also indicative of that water equivalence. It does have a minimal temperature dependence. It's about 0.1% per degree. This really doesn't come into play when it's all QA measurements at room temperature. But if someday we do step into the realm of more patient-specific measurements, which I should state we're not FDA cleared for at this point, but there may be some temperature correction that would need to be addressed at that time. And then the big advantage, which is of course the focus today, is that it can be used with MR-linacs. None of the features of that scintillation detector are ferromagnetic. They can be used within the field of an MR-linac or an MR irradiator. Really the configuration we've got now just is a longer fiber for this MaxSD or for the W2 so that the electronics can be kept outside the 5 Gauss line, just for safety purposes. The scintillation detectors themselves are organic scintillating materials. We've got the 1 millimeter diameter fiber. With the W1, it's a 3 millimeter long active region. And with the W2 fibers, there's both a 1x1 and a 1x3 millimeter detector fiber. The one difficulty with scintillation detectors, and the reason that they really weren't adopted into the mainstream dosimetry despite their long extended history of use in radiation measurement, is that there's this additional light that's generated, the Cherenkov light, within the optical transfer fiber. So this is the light that's being generated by the high energy electrons traveling through that medium, creating essentially like a shock wave of light, like you would think of a sonic boom from a jet traveling at supersonic speeds. So the method that we use for correcting our scintillators for this Cherenkov light, which is a stem effect, if you will, additional signal in the measurement, is a 2-channel chromatic correction based on a publication from 10 years ago now, I guess, Matthew Guyot et al., that defined this 2-channel correction. I'll show you that on the next slide, but here I also want to say that these are not absolute dosimeters. They cannot be sent into a calibration lab for calibration and then used for 2 years and expect them to be perfectly stable. The fiber is a plastic, it's PMMA. It degrades with radiation. And so that signal decreases as the fiber acquires more dose. Therefore, you do have to give it a calibration or a known dose in order to get a dose output rather than just a collected signal. And periodically recalibrate as it accumulates dose and as that sensitivity decreases. So the 2-channel method is kind of shown graphically here. We have a blue scintillator, and so the scintillation peak looks like this lower one here. Cherenkov is a broad spectrum contaminant. It is stronger in the blue region than the green, but there are other advantages to this blue scintillator. So the combination becomes this, of course, the larger curve. We split the spectrum into what we call the blue channel and the green channel, the blue portion of the spectrum, the green portion of the spectrum. And blue is primarily the scintillation signal, although there's a little bit of a tail that goes over into that green region. And what you can do with this is provide the system with 2 characterization measurements. The key point would be really that you're keeping the dose to the scintillator constant. And so this portion of the spectrum is not changing. The dose that's received at that active scintillator at the end of the fiber, but change the amount of optical fiber that's in the field. And that would change the level of this Cherenkov contribution. The Cherenkov change creates a change in signal in both the blue channel and the green channel. But based on the relative change in the 2 channels, you can create what's called a Cherenkov light ratio correction, or CLR. So it's just the difference in the signal in the blue channels between what we call a minimum fiber configuration, where you'd have the fiber coming straight out of the field. This is the slab for the W1 characterization. This is the jig that's used in the water tank for the W2. Minimum fiber configuration would come straight out. Maximum fiber configuration keeps that scintillation detector in the same position, but adds a bunch of the optical fiber to the field. Same thing here with this jig, where you wrap the fiber around. That's what this maximum configuration signal is from. So that gives you your Cherenkov light ratio. Subsequent measurements then can be corrected, removing that Cherenkov contribution by multiplying your green signal by that CLR and subtracting that from the blue measurement. And so that removes this Cherenkov correction from the blue signal, and you're left with just the amount of signal that comes from your scintillator. The dose calibration, if you'd like to give it that, to get measurements in terms of centigrade, really is just a dose or a unit conversion factor, a gain factor that's applied to this measurement. So you would give it a known dose in a reference field configuration where you've calibrated your machine, and then the scintillation detector or the subsequent scintillator measurements can be reported in terms of dose. So the W1 scintillator has been available since 2014. It has, as I mentioned, that 1 millimeter diameter, 3 millimeter long active area. There are a number of publications available for the W1, but kind of my favorite recently, probably the biggest one, is that joint publication from the AAPM and the IAEA on small field dosimetry. It's the Technical Report Series 483, which lists the W2 or W1, excuse me, in a number of the correction factor tables for various energies with and without flattening filters. But the W1 shows a KQ correction of unity in every single table it shows up in, which can't be said for any other detector that was looked at within this publication. You'll notice a couple of detectors if you pull out that paper or that publication and look through some of the tables. Some of the detectors don't show values in these very small fields, and that's because the uncertainty was too high or the stability was not good enough for that to be deemed appropriate, and so they couldn't report correction factors with the level of certainty that was required. The disadvantages of the W1, or I should say the limitations of this system, is that it was our first generation device. It was designed as a single point measurement system. This was really for output factor measurements from small fields. It was not designed specifically for water tank scanning. It does require a 2-channel electrometer, such as our Supermax, in order to perform that Cherenkov subtraction. We have routines built into the Supermax that help walk you through that and store your values so that you can use them for later measurements. But if you were to use a different 2-channel electrometer or even 2 single electrometers, provided you can synchronize the timing between the 2 of them, you would have to do those corrections by hand, where it's quite straightforward to use it with the Supermax. The W2 was the 2nd generation device, and it has a user replaceable fiber. We have integrated the optical signal detection system, as well as the signal processing electronics that used to be done with the Supermax within a single dedicated electrometer called the Max SD. This system allows you to do point dose measurements or Cherenkov characterization just with this system. You don't have to hook it up to any other electrometer. This helped us decrease the noise, electronic noise with the signal processing, which meant that we could also decrease our active region down to that 1 by 1 millimeter option on a scintillator fiber, so that you can get very uniform resolution without the volume averaging that happens over the 3 millimeter length of the W1. With this system as well, it will take that Cherenkov corrected value every 10 milliseconds from the scintillator and convert it to an analog output that can be sent to your water tank scanning system, so that you can collect the data with your water tank electrometer. So if you're scanning with the W2, you have to do your CLR measurements first with the Max SD. But once that file is saved as a calibration file, you would essentially just hook up the output from the Max SD to the input of your water tank scanning electrometer. And as far as your water tank is concerned, it behaves like a diode. You don't apply bias to it, but you receive current whenever the device is irradiated. These are pictures again of the minimum fiber configuration and maximum fiber configuration within the characterization jig that we provide. This is looking down into the water tank. And then this is a sleeve that we provide. I get lots of questions about this. How do I mount it in my water tank? We provide a sleeve. Basically, it's a stem adapter that allows the fiber to be held out away from the scanning components, so you don't get scatter concerns from your scanning arm. But it also allows you to use this in any water tank that will accept either a 7 millimeter diameter or 8 millimeter diameter scanning chamber. So any standard holder from any water tank vendor can be used with the W2 with this sleeve adapter that's included in the system. I think somewhere, I guess I was talking and not looking at my notes quite so well, but what I meant to say was that for the W2MR, It's probably the prior slide. There we go, the W2MR. The configuration, the only difference really between the W2 and the W2MR specific configuration is that this W2 fiber is longer for the W2MR, so that the max SD can be outside that 5 Gauss line, and you can have the slack that you need to be able to configure it in whichever phantom or water tank you're measuring in. One thing to remember with the MR use of this within an MR field is that the way the Cherenkov signal is produced, it does have a preferential production angle based on the direction of travel of the electrons. And so depending on your B field orientation, you may or may not be directing those electrons a little bit more down the fiber of the W2, which can increase the contribution of your Cherenkov. It doesn't seem to change the spectrum significantly, but it is best, if possible, as you're doing your characterization measurements, to try and make sure that you're oriented within the B field in the same way that you would be for the measurements of the fields that you want to make. So just something to keep in mind there. Some published data about the W2. This is one of the first publications from Paulina Galavis at NYU Langone. They looked at the behavior of the W2 relative to the to film as the gold standard for the scanning, but also just to make sure that none of the behavior of the scintillator itself had changed from the W1, so that the publications on the W1 could also apply to the measurements that you're making with the W2. So they looked at dose rate dependence, they looked at dose dependence, I believe they looked at temperature dependence as well. But some of those things were shown to be the same between the W1 and the W2. We didn't expect it to change. It is exactly the same fiber constructed in exactly the same way. The only thing that really changed was our optical detection system being combined with the signal processing electronics. Another publication from a couple years ago, 2019, I guess, was Richard Popple's group, Jesse Snyder, down in University of Alabama at Birmingham, where they looked at smaller, decreasing size targets with their variant hyperarc system, and the agreement between the W2 measurements and their film measurements for patient-specific target measurements. And they found excellent agreement with film dose for targets down to 3 millimeter diameter target, which was the smallest one they evaluated. Let's see. Oh, and I was going to say the images on the right here show the chamber plug that was used within their phantom. And with the W2 being water equivalent, you can't really pick out the tip very well for targeting. So we do also provide a localization marker that really is just a dummy fiber with a BB at the active point of measurement that matches the scintillator, so that you have something either to align to with your image guidance or to plan to. There are a few posters I'm aware of at AAPM. This output constancy in FFF fields is an interactive e-poster. So that's tonight from 5:30 till 6:30 Eastern time. These others are just standard e-posters, and so they're available for browsing at any time. And hopefully I haven't forgotten any, but if you're on the talk here and I've forgotten your poster or your presentation, please let me know and we'll make sure to include that in our AAPM booth. But speaking of which, please, if you are attending AAPM, stop by and visit our booth. These virtual events have been pretty tough for vendors as a virtual booth, but we'd love to have you stop by just to say hi, say you were here at the talk, and you whether you want more information or not, we'd love to hear from you. If you do want more information on any of these scintillation detectors, our website is shown here with the AAPM landing page, but you can get there, get to any of the product info that you want from there or to our virtual booth. Or feel free to reach out and contact us, find your sales representative, sales@standardimaging.com. And I would happily entertain any questions if you have any now. Otherwise, thank you so much for your time. We look forward to seeing you again in the future. The question from Vincent is, have you used the W2 for measuring output factors? Yes, the W2 can certainly be used for measuring output factors directly with that max SD. You can do point measurements with it. I'm sorry if that was not clear. The W1 was designed specifically for output factors. The W2 just built on that so that it could also be used for scanning. Yes, absolutely use it for output factors. I'm not seeing any more questions come in. So once again, thank you everyone for your time and enjoy the rest of the AAPM meeting.